Well, thank you very much. As I was saying sort of informally before we started, oh, by the way, I guess being the camera being what it is, I probably need to stand here and not move around a lot, or? I can move the camera. Oh, okay. Then I'll make you chase me. The purpose of this really, I guess, is to discuss liquid rocket engine development in general, perhaps centering around SSME because it's sort of dominated the scene, at least in the manned space flight world for the last 30 years, but would be fully prepared to talk about other systems too. If anybody, I'm going to try to keep this simple enough and generic enough that hopefully will build some momentum and lead to people asking really good questions. And that'll lead us through. If people want to talk about foreign systems, including Russian stuff, I'm somewhat equipped to discuss that. So don't be shy. We're going to start by beholding the magnificent. This is the so-called Block 2 Space Shuttle main engine. Our discussions of the shuttle main engine are not going to, they're not going to discriminate between Phase 1, Phase 2, Block 1, Block 2. It's going to be the SSME in general.
Is this the one that they ended up flying last?
As far as I know, yes. It's got the so-called Pratt & Whitney turbo machinery in it, and 2 or 3 other modifications that were not there early on, although frankly, if I didn't bring that up, you probably couldn't tell. The SSME was, to say the program was extremely challenging would be probably the understatement of the year, at least. And the challenge was brought about by the fact that this thing was different in a very fundamental way and was approached in a fundamentally different way than any engine that I'm aware of ever before. Previously, and I'm talking about, this was largely in the era of ICBM development and development of the launch vehicles that everybody knows as the Saturn system. Development of engines began anywhere from significantly to considerably in advance of development of the vehicle, such that by the time the development of the vehicle started, and the vehicle people went to engine people and said, we want an engine, and the engine people would tell them, you can have any engine you want as long as it's this one right here. SSME pretty well turned that around. By the time development started on the SSME, and if somebody is here who was around in the 71, 72 time period, which is before my time by a handful of years, they could probably argue contractually with this, but I'm talking about from a meat and potatoes substance point of view. The vehicle that you know as the Shuttle orbiter was, for all intents and purposes, frozen as a thing before this machine was developed. So SSME was more or less completely specified. Its attributes were completely specified by its user, which was the space shuttle. I'm talking about, in particular, if everybody here can bring the shuttle orbiter to mind's eye, right? There were 3 of these things sitting in the aft fuselage of that vehicle, and when I say the orbiter was already pretty well a thing, what I really mean is the physical extent of that aft fuselage was frozen. It was known, and we had to fit 3 of these things in there, with room for people to move around. This thing had to produce a fixed amount of thrust, 475,000 pounds in a vacuum under normal conditions, 512,000 pounds of thrust in a vacuum under so-called emergency conditions. It had to produce a given amount of specific impulse. Does everybody here know what specific impulse is? And when I say to everybody, if I use terminology that somebody's not comfortable with, just stop me and we can talk about it. Specific impulse is essentially the liquid rocket's equivalent of gas mileage. And the engine had to weigh no more than this much. Now, specifically, the specific impulse that had to be produced was on the order of 6 or 7% higher than the biggest hydrogen engine we'd ever built had ever produced before. 6 or 7% may not seem like much, but in our world, people would sell their mother for 0.5%. So when you talk about an order of magnitude more than what you'd let mom go for, this was tough. In addition, the weight specification of the thing was that one of these things had to weigh 6,500 pounds. Now, to give you sort of a broad overview of where we ended up, by about the summer of 1985, which was when the original lineage of this engine was sort of at its peak, and we were sort of as on top of our game as we got, this engine was producing the required amount of thrust, which it did because the control system made it do that, and was producing that at a specific impulse that was anywhere between 2 and 4 seconds short of the original targets, and was at very best 500 pounds overweight. We had a contract end item specification target of 6,500 pounds. The best it ever got was 7,000, and it only got worse from there. That was when we started putting improvements into it. Those all translated into weight increases, and most of them large ones. So it's fair to say that even though this thing never disrupted launches to an overly great degree, we were operating at the fringe of what was doable. Yes, sir.
Is it okay to interrupt during the...
I would encourage it.
Okay. So you said you were chasing improvements during the course of the engine program. Were you going after performance improvements or reliability improvements or what? All of that.
Yeah, by the time summer of '85 rolled around, it's hard to chase a lot in the way of performance improvements when the pedal is already to the floor. I mean, when you're doing all your car will do, it's tough to do more. Most of the improvements that were sought after '85, and if anybody can think of anything to the contrary, my memory's not always perfect, but most of the improvements that we sought after that were maintenance and reliability centered. Yes, sir.
In an environment like that where you're trying to trim every pound, how do you do safety factors? I mean, doesn't every one of these subsystem guys want to tack on a big safety factor? how do you
Call it a yes.
I mean, everything's bigger than it needs to be because they don't want it to blow up, right? But then how do you trim all that back?
Well, let's see. Let's talk for a minute.
Was there that kind of finger pointing where someone said, "Oh, you're totally deep in this thing"?
No. You think? Let's talk for a minute about safety factors. For the most part, what the gentleman is talking about with regard to safety factors are largely structural safety factors. Now, this engine was a little different from previous ones in that, of course, it was reused. Our original contract requirements, and I don't pretend to remember how they might have changed. I'm not sure that in this instance they ever did. But our contract requirements were, is there anybody here that, are people here familiar with the concept of fatigue? I mean, not us, but in hardware. The idea is that a part of the engine might be able to take a certain load, a certain amount of stress, the first time it's used. The 10th time it's used, if it's subjected to that kind of load again, it may fail. And the point at which it fails, when the applied loads on it are kept where they're supposed to be, is referred to as a part's fatigue life. We had a contract requirement for a fatigue life for everything on this thing of 55 flight cycles. And I don't know if that ever got circulated in the outside world, but the idea was 55 flight cycles. And not only that, we had to have what we called a safety factor of 4, which was really, in order to achieve 55 flight cycles in the presence of all of the unknowns, i.e. the environments to which the thing is subjected may not be what you think they are. We took those 55 flights and multiplied by 4. So everything was designed ostensibly to a fatigue life of 220 flight cycles. Given that and materials and fabrication processes and all that, pretty well defines the levels of stress to which a part can be subjected when it operates. Now, there's lots of little things that flow from that, but that's the basic idea.
Everyone just agreed on those, and then
It's not a question of whether we agreed on them. They were thrust upon us by the contract. And when parts were designed, we had to show with the greatest analytical rigor possible that we met those requirements. And that's why, for example, the housing of a pump was as thick as it was.
So Dave, when they refurbish those, I know, what did they pull out, what did they do on that block diagram, what didn't get used in the end on the next time around?
Well,
Did all that hardware really get used for all those flights, or did some stuff get thrown away?
there wasn't anything that was considered expendable on a routine basis. There were
Not seals or raceways?
well, okay, seals for the large part were considered expendable, but I mean seals were considered to be bench stock, almost like bolts or O-rings or that sort of thing.
But they would pull this out, what would they do when they pulled it out before they would, and then reinstall or?
We only have an hour.
Big picture, big picture.
Well, largely for everything that was going on in this system, the greatest action was in the so-called high-pressure turbo machinery, HPFTP, high-pressure fuel turbo pump. This is a 3-stage centrifugal pump driven by a 2-stage hot gas turbine that pumps liquid hydrogen, about 160 pounds a second or so, which is something on the order of 16,000 gallons a minute. In at about 270 psi, out at about 6,500 psi. And
What kind of chamber pressure were you running there?
3,000 pounds. The highest before that was the F1, which was a little under 1,000.
Was there a big difference in the turbo design between the oxygen and the hydrogen side?
Oh, yes, enormous. And this machine, the high pressure fuel turbo pump, probably yay big around and yay high. The original Rocketdyne version of the pump weighed on the order of 700 pounds. And at the thrust levels we fly at, the turbine would produce and the pump would consume. Everybody understand in a turbo pump, a pump needs power applied to it like your swimming pool pump needs an electric motor. The power is supplied by a hot gas turbine, so the turbine supplies power, the pump consumes it. The power supplied or consumed here, depending on how you want to think of it, was about 75,000 horsepower. Yeah, yes, sir.
At a high level, the original design of the shuttle was that the motors, engines were not supposed to be removed after each flight.
That's a true statement.
Okay, but then they ended up being removed after each flight, and
That's also a true statement.
replacements would be pushed, refurbished ones would be pushed back in, I assume.
Yes.
Okay.
Let's take. We'll take that in a little bit of detail here. Bob.
How fast did they spin?
Oh, I don't know if he knows and just wants me to say the number or what, but the high pressure fuel pump at the thrust levels we flew at turned about 37,000 RPM. The impellers in the pump end were right at 12 inches in diameter, and if you work the numbers, the tip speed of the rotating impellers was right at 2,000 foot per second.
What were they made of? Like enamel or
Titanium.
pure titanium?
No, not pure titanium. It's one of the alloys, and I don't remember which one it was right off. Yes, sir.
How much different is the expendable design they're coming up with? Is it just basically lightened up, or?
No, as far as, well, when the expendable, I'm not in touch day to day with the expendable design they're coming up with, but the times of this that I've been in touch with, boy, all these questions they have a lot of tentacles to them. In the first place, you got to understand that all the manufacturing capacity for this thing is gone. So when you hear people talk about restarting production of this thing, the question is how, where, with what, and with whom, because everything is gone. Now, the expendable version probably, expendable versions that I've been in touch with are different, almost not at all. A lot of us that worked on this thing like to joke after hours and sometimes during hours that this thing is the best parody of this thing would be a big mean-looking bulldog with one of those collars that has spikes on it and a sign hanging around it saying, "Don't mess with me." Once we got it the way that worked, everybody was loath to change it, to change anything, because changing anything invariably made something not work. Now, having said that, the expendable version of this thing, at least the one that I was in touch with, the hardware basically doesn't change at all. What does change is that in order to fulfill our contract requirements with the government, one of which, a major one, was reusability. Rocketdyne, had an enormous fraction of the workforce that was dedicated to nothing but the bookkeeping task, making sure that for the three engines that were in that vehicle out on the pad that's going to fly, and by the way, everybody understands, don't they, that every part in this engine, down to the last turbine blade in that pump, has a serial number etched in it. Every last part. And every last part is tracked through an omnipotent database that knows what that part has been subjected to, how long it's been subjected to it, and ultimately how much lifetime that part theoretically has left in it. You know, since I'm being videotaped, I need to limit the controversial nature of what I say, but it is probably not an overstatement to say that if you drop the reusability requirement for this thing, the cost of one would probably be cut by somewhere between a third and a half. And it's not changes in the hardware, it's just the number of people doing jobs.
It was just a single turbine driving both turbopumps?
No. The turbo pumps are separate. Separate gas generators are what we call pre-burners, and a separate turbine. I'll show you close-ups of the original versions of these here in a minute or two.
Gas generator cycle, isn't it?
No, and we're going to get into that too. It's a fuel-rich partial flow stage combustion cycle.
How much is the new J2 drawing on the original J2, and how much on this technology, the J2X?
Well, I haven't had any contact with the J2X for a year or so, but you know, the J2X is a gas generator cycle engine, therefore it has a huge family resemblance to the J2. Upgraded turbo machinery that were used in versions called the J2S are what's being used in the X. So it's much more like the original J2 than it is like this. Although there are some parts to the X, like the main combustion chamber, that if you put an SSME combustion chamber on a table and a J2 combustion chamber on a table and put an X over here, you would say, oh, the X looks like the SSME. Now, a fellow asked about the engines being removed and all that sort of thing, the fellow in the gray shirt there. Let's touch on that for a minute, and if it's not gray, I don't see color very good. The original concept was that engines would remain in a vehicle after flight and would undergo whatever minimum maintenance tasks were required between flights. There was a period at the beginning of the program where we worked it that way, and I mean there was no technical reason why that could not be accomplished. And in truth, one of the reasons that we kept the engines in the vehicle and flew the same engines time after time was we had no spares. As we proceeded with the program, the operational conflicts day to day between what the orbiter people were trying to do and what the engine people were trying to do, and the engine people invariably needed support from the orbiter people in one form or another to do a particular task. Like if we wanted to leak check the liquid oxygen system, the pressure that we had to put into the system, which was 25 psi or so, needed to be supplied by the orbiter. And so the orbiter had to have people and had to have themselves configured to support us. And we increasingly got to being at loggerheads day to day. And we soon found out that taking the engines out after a flight so that the engines could be worked on independently was a much more operationally efficient way to do things. Yes, sir.
So when Endeavor was commissioned, were new engines ordered, or did they use engines on hand?
Well, I don't remember exactly. I mean, we were in as close as we ever got to full engine production mode at the time. So I'm not sure that anybody ever really would have known the difference. Yes, sir.
What was the efficiency? You know, your delivered IST versus theoretical.
I'm going to take it.
At 100% power.
I'm going to take exception to your use of the word efficiency. Efficiency in the propulsion and power world is probably one of the most overused and least understood words, and it's terrible. Efficiency is normally used in conjunction with power plants that produce power, honest to goodness power. And in one way or another, efficiency of an entire integrated system is typically the rate at which work is produced by that system divided by the rate at which work is infused into the system, which is typically chemical energy in a fuel. So, you can think of it as horsepower out in terms of work divided by horsepower in terms of the rate at which fuel is going into it. So, now having said that, not to sidestep the question, the original design intent of the engine was to produce 455 seconds of vacuum ISP. Now, talking about what is the produced ISP, that's tough. Is everybody familiar with the idea that ISP is thrust divided by flow rate? Both.
What was the design altitude of that engine?
I'm not sure that there was one, only to say that the thing is technically an upper stage because it's got a nozzle on it with an area ratio that is absolutely not conducive to running on the ground. If any of you have ever seen slow motion photographs of the startup and seen what the startup transient does to this nozzle in terms of motion, the thing is clearly an upper stage.
So it was severely overexpanded at sea level?
Oh, the core nozzle exit pressure is like 2 psia. I mean, we were lucky to get it to start. Now, back to the ISP question. Actually knowing what the ISP produced at altitude is, there's vagaries associated with that, and nobody's ever really sure about the altitude ISP that they compute, and it's computed from flight performance, from what the vehicle does. But you got to understand the data that you use to compute that largely comes from the guidance system, and the guidance system is only going to tell you what a great job it's doing. So now, having said that, the ISP produced by these things, again, if somebody was there and has one particular incident in mind, they might argue with this, but the numbers typically varied between 451 and 453. So, I mean, in absolute terms, we were quite close. But you have to remember that as program management people gain more confidence in the system, they start trying to make a living by flying more and more missions that are just barely possible. And so thinking that we know the produced ISP down to within a second or so becomes progressively more important to people. Did we really know it? Maybe. Probably the best indicator of that was, did we ever run out of propellant on the way to orbit? And the answer was yes, that happened to us 2 or 3 times. Yes.
I was in the program.
Yes, you do.
And I remember when I talked to you about it, they would be picking engines for specific missions based on ISP. Oh, well, this one we need another second, so we'll take this engine. This engine.
Yep, that's a true statement. There was times when we did that. Yes, sir.
So, yeah, just to follow up. So the other comment you always heard was, throttle up to 105. So I'm sure that they had that was set by temperature limits, how long they could run at beyond 100%?
Okay, yeah, this is an interesting question, and I'll sleep better tonight actually getting this revelation out to the world. You heard people say, particularly news commentators, give the impression that, when the mission commentator would say engines are at 104% or whatever it was that week, that somehow we had found that 100% thrust wasn't enough, and we just sawed away the floorboards and pushed the pedal past the floorboards and damn the torpedoes and full speed ahead. Well, that's not the case at all. And the simple fact, as usually happens, is it's a terminology thing. Back when this engine was originally envisioned, there was a thrust level associated with it for a nominal mission. And I'm sort of going back to the original Rocketdyne only version of this engine, so you got to kind of think past, is this a Block 1 or Block 2? We're talking about the original version of the engine and the original intent. There was a thrust level assigned to it at which it would fly its nominal missions, and you've got your brow furrowed like I've confused you. Did I say something that, no, the fellow in the yellow jacket?
No.
Oh, okay.
Just thinking to myself.
That thrust level was deemed to be 100%. You'd also hear it called rated power level, or RPL, or 100% RPL, or words to that effect. Also during the system definition then, when the people in Houston were psyching out how was this engine going to play with their vehicle, and the people in Houston are extraordinarily motivated and extraordinarily thorough people. There are other words for that. And one of the scenarios that they play through is that if one of those three engines fails and they can't get to where they're going and they have to do what everybody knows as an abort, how's this going to play out? During these mission studies, and again, this was before the engine was even really designed, it was determined that if the engines could be throttled up from their nominal thrust level by 9%, that for their selected abort cases that they were wanting to zero in on, that this would keep the crew out of the water. So that, and did I say something there? No? Okay. So that thrust level became known as, perhaps as you'd predict, 109%. And became known as the emergency power level, or EPL. Now, in fact, the way this really worked was the original design point for all the hardware in this engine, because it was our deduction that if you throttle this thing up to the emergency power level, you really need it to work. All the hardware in this thing was designed to sing along together in an optimum manner at their so-called design points at 109%. So the actual design point of all the hardware in the engine was 109%. And the 100% rated power level was considered to be a somewhat derated condition. And by the way, a condition at which the hardware would last longer.
Trying to tweak your specific impulse, you mainly played with characteristic velocity changes?
I don't know what you mean by played with characteristic velocity changes.
CF times C star.
C star of the propellants are what they are. I mean, when you burn LOX and hydrogen at...
The only other option was the nozzle design itself.
Okay, now and again, I'm not trying to be too forensic here, but when you talk about trying to tweak the ISP, once we got a design of the nozzle that worked, it was never played with. As a matter of fact, a nozzle person would tell you that the final design of that nozzle that flew was bad. And the reason it was because the original design that was, quote, good was not structurally sound. We had to mess with the contour to get it to hold together, and as a result, it was not shock-free inside. And we paid some CF efficiency penalty, like on the order of 0.5%. When we talk about tweaking ISP, again, once the hardware designs were set, there wasn't a lot you could do to tweak ISP, and something that I'm hoping we're going to have the time to get to here. How long have we been? God, we're 2/3 done already. If anybody's ever heard of the different cycles like gas generator versus stage combustion, in a J2 type engine, in the so-called gas generator cycles, the exhaust powering the turbines goes overboard, and it is considered a loss. You can increase ISP of the engine if you can decrease that turbine flow that goes overboard. In the shuttle stage combustion cycle, everything goes through the main thrust chamber, and so everything basically goes into producing thrust. There's a couple of things that you could argue, technicalities, but in the real world, essentially everything goes through that main combustion chamber and produces thrust. Therefore, if we talk about can you tweak ISP, you really can't. There's no knob to turn. There's nothing. There's no place you can go and say, I can fix this.
Are there problems with combustion instability issues during the design?
No, thank heavens. The Saturn F1 program, the Saturn V first stage booster engine, had undergone combustion instability problems that required 2 or 3 years of national priority level funding to fix. The combination of Rocketdyne and Marshall Space Flight Center were still smarting from that when SSME was being designed. And so from a combustion stability point of view, all the stops were pulled out before we ever even started. Now, in fairness, you also have to go back and say what we found out after the fact is that the combination of liquid oxygen and I'm hoping we can get into the cycle stuff here, but suffice to say that the hydrogen that's burned in the main combustion chamber is not raw liquid hydrogen off the hydrogen pump. If you follow the flow schematic, you'll see that basically all the hydrogen goes to the 2 preburners that drive the 2 high-pressure turbopumps. Inside each preburner, that hydrogen is burned with just enough oxygen to heat the hydrogen up to the temperatures required to get the turbine power to drive the cycle and hold everything together. And to give you an idea, in the preburner that drives the hydrogen pump, the so-called fuel preburner, about 10% of the hydrogen that's injected into that preburner is actually burned. The remaining 90% is not burned, it just gets heated by the combustion reaction of the other 10% and the oxygen. In the oxidizer preburner, the target temperature was a little lower, so that the amount of hydrogen that was injected in there that actually got burned was only about 6% of the hydrogen that went into it. As a matter of fact, that preburner was fundamentally cantankerous because that amount of hydrogen getting burned, 6%, was so small that we were essentially trying to light hydrogen and oxygen at or below the fuel-rich blowout limit. and that introduced its own difficulties. So this gas, which was technically termed hot gas, strangely enough, drove the two high pressure, that was a joke, by the way, drove the two high pressure turbines, and then this exhaust, which was mostly unburned hydrogen at temperatures on the order of from 1200 to 1500 degrees, goes into the main chamber injector where it is burned with raw liquid oxygen off the oxidizer system. And the reason I'm going into all this is that what we found was the combustion combination of LOX and hot gas when burned in a, anybody here seen the injectors that were used in the J2 and SSME concentric element, so-called tube within a tube, or coax injectors? People are shaking their heads, and unfortunately we're not going to have time to go into it, but there's a particular injection scheme that's used for LOX and hydrogen that was actually pioneered in this country by the NASA Lewis Research Center back in the 60s, back in the 58, 59, 60 time period. It's a tube within a tube, and liquid oxygen comes out of the inner tube, hydrogen comes outside the inner tube but inside the outer tube. And it's referred to as a coaxial or a coax arrangement. The coax element that's used here in combination with the LOX and hot gas propellants were actually found to have a positive margin of stability all in and of themselves, and from what we could tell did not require the stability aids, the baffles and all that stuff. We went into it with the injector having baffles on it, either because we thought they were necessary or because Pratt & Whitney's version didn't have it, and we whispered in Marshall's ear and said, look at ours, we've got it. And you know, it was found at least partway through the program that, you know, we probably didn't need these, and like everything else, you know, we were absolutely loath to change it, but ultimately later in the program they came out. We're on a roll with questions here. Any? No? Okay. Well, let me, we're actually in about the last quarter of this thing. Why was this thing so different than what had gone before? Well, I'm going to show you. Okay. This drawing, which I know looks probably like first prize in an 8th grade art contest, I teach a propulsion system design course for one of the Beltway Bandit outfits, and this is part of my material. An engine like the J2 or an engine like the F1 or an engine like almost all of the systems that came before SSME operated on a scheme whereby there's oxidizer and fuel present in the tanks of the vehicle. They feed pumping machinery. In this case, oxidizer is pumped directly from the oxidizer pump, typically through a valve, into the injector of the thrust chamber. And typically in a system like this, the outlet pressure of the oxidizer pump, in order to overcome the losses along the way, will be something like 1.3, 1.4 times the rocket motor chamber pressure. The fuel is pumped by a pumping element, typically again through a valve, this is my attempt to portray a regenerative cooling system. Typically, nozzles are cooled with fuel. That fuel then goes straight into a fuel injection system. And partway along the way, there are tap-offs for oxidizer and fuel that go into a small auxiliary combustor called a gas generator, which makes hot gas, typically at relatively low temperature and rich in fuel. And that hot gas, which is basically the pressure in the gas generator, is typically on the same as on the order of the main chamber pressure. And that gas expands through a turbine and ultimately basically goes to atmosphere. Again, there's some places where purists would argue, but so the turbine basically has gas available to it at perhaps a little less than chamber pressure and atmospheric pressure on the downstream side. If any of you are into machinery, the turbine functions according to a thing called the pressure ratio, the ratio of the inlet to the outlet pressure. In a gas generator cycle engine, that pressure ratio might be a number anywhere from 10 to 50. And you know, numbers like 10 to 50, I mean, those are high pressure ratios. There's not many industries besides rockets that typically deal with turbines that have pressure ratios that high. There are typically some stages in a steam turbine in a power plant that do, but the difference in the working fluid between the steam and this hot gas, is it something I said, Matt?
No, I still got to do something else.
Oh, okay. Anyway, the idea is that the pressure ratio of 10, 20, 50 across a turbine it's fundamentally tough to make a turbine perform. The fuel pump will typically have to produce outlet pressures on the order of 1.5x of chamber pressure.
Was that turbine gas vectorable or?
No, not usually. In Delta IV it is, and some of the early versions of the Titan was, but not as a rule.
I'm sorry, what was the question?
Whether the turbine exhaust gas was vectorable, and the answer was 80% of the time no. Okay, now, as Cosby would say, I told you that story to tell you this one. Okay. That stuff that was going out the turbine represented anywhere between 3 and 5% of the total engine flow. Therefore, it was a loss. And that loss of specific impulse of between 3 and 5% was, by the time the shuttle came around, was more than people wanted to put up with. So the engine system that was stipulated by NASA was this thing called a stage combustion system. Now, what's this stage combustion system? Well, if you notice here, the oxidizer pump does pump to the main combustion chamber just like before, but it also pumps to a second oxidizer interface, which is at this thing called a preburner. Preburner is basically it's the same as a gas generator in the gas generator cycle engine. One of the reasons we earn so much money is we change the name of things. So there is some oxidizer, about 10% of the total load, sent to a preburner. The fuel system pumps through a regenerative coolant system just like it did before, but from there into the same preburner, where fuel and oxidizer are burned at the same kind of temperature as in the gas generator cycle engine, more or less. And that exhaust gas used to drive a turbine. Now we're showing only one turbine here, but this is intended to be a conceptual thing. The turbine exhaust then, with being mostly unburned fuel, then goes to the fuel side of the main thrust chamber injection system, since this gas is mostly unburned fuel. And hence the use of the term stage combustion, meaning that combustion of the fuel happens in two stages, here and here. Well, there's a fundamental difference in these systems. What is it? If we look at the gas generator system, the outlet pressure, the back pressure for the turbine is basically atmospheric, 14.7 or less. In addition, that back pressure essentially doesn't change from before the engine starts to after it starts. In addition, you'll notice that the gas generator and the turbine, they operate essentially in parallel with the main thrust chamber, i.e. the same pump pressure that services the thrust chamber also services the gas generator. And by the way, in the J2 engine, the original J2 engine, this pressure in here was on the order of 800 psi. Now we want to build a shuttle engine. And this thrust chamber pressure now is increased from 800 to 3,000 by a factor of almost 4. Not only that, but look, what's the back pressure of the turbine? The turbine back pressure is ultimately the chamber pressure of the engine. And that turbine back pressure starts out as atmospheric before the engine starts. But in the process of starting and lighting the chamber, that turbine back pressure goes from 14.7 psi to 3,000 psi in a matter of 3 seconds or so. And all that is a lot dirtier than it may at first sound. So and by the way, if you look also in this system, the preburner, which is like a little rocket motor by itself, and the turbine, both of these have high pressure drops across them. They're not in parallel with the chamber anymore, are they? They're in series with it. Everything in this engine empties into the main chamber. The main chamber pressure is the ultimate back pressure of that system. And this means that the oxidizer system pressure, which was in the J2 on the order of 1,100 psi, now in the SSME oxidizer system has gone to 7,800 psi. The fuel system pressure, fuel pump outlet pressure in the J2, which was 1,200, 1,300, 1,400 psi, is now 6,600 psi. In order to go across all these pressure drops in series and make it here at 3,000 psi. And I'm here to tell you, oxygen systems with pumps in them that work at 7,800 psi are inventions of Satan. By the time we finished the testing on the first serial number 1 SSME, it is not an overstatement to say that I don't believe there was one part in that high pressure lock system that had not burned at one time or another. That high pressure lock system, the pressure at which that lock system operated drove everything. It drove the selection of materials. It drove the radii of curvature of the piping. Sharp turns are places where particles can impinge on a wall at high velocity and ignite. I'm telling you, it was brutal.
Is the engine control mechanical, computer? What actually is the engine control for this?
The engine control is done by an onboard computer, which interrogates instrumentation on the thing 50 times a second. And the control is by the adjustment of 5 valves. And I got to watch myself or I'm going to start running overtime here. But There's a main fuel valve, a main oxidizer valve, oxidizer valves at both preburners, at the fuel preburner and the oxidizer preburner, and a thing called a chamber coolant valve. Those are all ball valves, and they have actuators on them that are driven by hydraulics. And the controller controls the actuators of these valves and basically moves the valves around to make the engine do what it wants. Yes, sir?
You have time to briefly tell them about the time when the plugs got nicked the hole in the nozzle and screwed up the engine ratios and everything?
Well, okay.
I don't know if you got that one.
Go ahead.
By my watch, I've got 2 minutes.
We're enjoying it, so if you went a little longer,
Oh,
go for it.
yeah, but the next presenter wouldn't. This actually happened on Eileen Collins' first flight as CDR, poor lady. And this will show you how non-intuitive operation of this thing can be. We had done repair to 3 or 4 injector elements, which meant driving plugs up into these injector element tubes that almost looked like gold-plated golf tees. Well, during engine start, one engine spit 2 or 3 of them out. And they dinged the inside of the nozzle on the way out. And the nozzle's made of tubes, 1,080 tubes. Each tube's basic diameter is 1/4 inch. It's made of A286 stainless steel, and their wall thickness is on the order of 10,000ths of an inch. I mean, they're thin-walled. And the bottom line was we punched a handful of holes on the inside of the nozzle tubes. Well, these things are taking hydrogen off the fuel pump to cool the nozzle and go into the preburners. Well, now all of a sudden, the system is leaking fuel. What happens when the system leaks fuel? Well, when fuel no longer goes to the main injector to be burned, but it's leaking here, the system is starved for fuel, somewhat. And so there's a drop-off in main chamber pressure. Does everybody understand that? Okay. How does the system respond to a drop-off in main chamber pressure? Well, the answer is obvious. It cranks the oxidizer side of the engine, because the way the control system, the engine chamber pressure responds most vigorously to oxidizer, because oxidizer is about 85% of the total flow. So the system sees a chamber pressure drop off. It cranks up the oxidizer side, increases the oxidizer flow. The fuel flow is measured by a turbine flow meter right here, upstream of the main fuel pump. If the leak is here, the system can't tell from here that it's leaking fuel. So when it leaks fuel, gets a chamber pressure drop off, cranks the oxidizer side to restore the chamber pressure, and the computed mixture ratio comes out just, hey guys, I'm doing fine. He's actually running off mixture ratio. He's running high. His LOX flow rate is high, and we depleted LOX on the way to orbit. Not by a tremendous amount, but it required an ohms burn. You know, people would think, well, if you're leaking fuel, how could you run out of LOX? Because you must have to do something to boost the fuel flow. That's not how the control system works. And the control system is very simple-minded. Well, I'm afraid I've gone over a little bit, but thank you very much for listening. If you like what you heard, my name is Dave Mohr. If you didn't like what you heard, my name's Pat McCarthy.